Greetings, chemists. Today we're going to talk about acids and bases, particularly strong acids and bases, and how to calculate pH and pOH. So here we have an image I found online from Khan Academy of the pH scale with some various common things you might know on the pH scale. So the pH scale ranges from 0 to 14. As you can see on the left side here. And 0 to 7, this area is going to be considered acids, and then 7-14 is going to be considered bases, with 7 being neutral in the middle. The Bronsted-Lowry definition of an acid and a base is shown in the example here. So here we have NH3, which is ammonia, added to HCl hydrochloric acid to yield NH4Cl, an ionic compound. So the Bronsted-Lowry definition of a base is a proton acceptor. So here we have NH3, ammonia, acting as the base, and HCl is acting as the Bronsted-Lowry acid, and Bronsted-Lowry acid being a proton donor. I put the proton, and proton's H+, I put the proton in pink here to show you that this proton here is going to get donated from the HCl, and it's going to come over here and get donated to the NH3. And I included the Lewis structure so that we could tie this to what we had previously learned, seeing how this H is going to leave the Cl and come over and join in here, as you can see with this resulting Lewis structure. So strong acids and bases ionize completely. And what that means is that they break up into their ions. So for example, HCl, which is a strong acid, is going to break up completely into H+ and Cl-, meaning it ionizes completely when it's placed in water. Strong bases are soluble metal hydroxides, meaning metal hydroxides that dissolve in water, and here are a bunch of examples. So there are 6 strong acids that are all listed here, so you should make sure you record these and memorize them. And again, the strong bases are the soluble metal hydroxides. Notice that metal hydroxides, these all contain a metal, which is the cation, and hydroxide is OH-, so notice they all contain the OH- anion. To show an example of how these strong acids and bases ionize completely, I'll do one example of an acid and one example of a base. So here's the example of the strong acid HBr. So if we have 0.12 molar HBr, now 0.12 molar is the concentration of HBr. So molar stands for moles per liter, so it's the amount of moles of HBr per liter of solution. That's just a little background on solution chemistry. So if we have 0.12 molar HBr, when you place that in water, when you put it in water, which is what this is representing here, they're going to separate, these ions are going to separate into H+ and Br-. And particularly, you'll have 0.12 molar H+ and 0.12 molar Br-, because HBr is represented here as 1 H, remember there's the invisible 1 here, and 1 Br-. So there's 1 H+ and 1 Br-, so the concentration of the H+ is 0.12 molar, and the concentration of the Br- is 0.12 molar. Now to show an example with our strong base, I'm choosing the base CaOH2, and hopefully you'll see why I'm choosing CaOH2. So our positive ion here is Ca2+, and our hydroxide, again, is OH-. And if we have a concentration of 0.14 molar, which I just made up, if we have a 0.14 molar concentration, notice that when it ionizes completely in water, shown in this beaker down here, it's going to ionize into Ca2+ and OH-, our cation and our anion. However, notice that in this formula here, there's one Ca2 plus, but there's two OH minus ions. So when this ionizes in water, we have 0.14 molar Ca2 plus, but we have 0.28 molar OH minus. How did I get 0.28 molar? Well, if there's double the amount of OH minuses in one CaOH2, then I need to double the concentration. Because when this CaOH2 ionizes in solution, it's going to break up into one Ca2 plus and two OH minus ions. So there's double the concentration of OH minus ions, hence the 0.28 molar OH minus. Now these ideas presented here in terms of acids, strong acids and bases ionizing in water and their concentrations, that's going to be important for calculating the pH and the pOH, which we will do on the next slide. Here are all the equations you will need for calculating pH and pOH for strong acids and bases, which was what we're focusing on today. So pH is equal to negative log of H plus. And this is a log base 10. And the concentration of H plus is equal to 10 to the negative pH. So the concentration is denoted by these brackets. These brackets actually mean concentration. And the concentration is going to be in molars, which is moles per liter, as I said on the previous slide. And this first equation here, if you are familiar with probably Algebra 2 level math, this second equation comes from the first equation using the log base 10. If you're not familiar with that from algebra, then just feel free to memorize both equations. But again, the pH is equal to the negative log of the concentration of H plus ions, or the concentration of H plus ions is equal to 10 to the negative pH. And pH does not have a unit. And just for your understanding of how this logarithm works, the higher the concentration of H plus ions you have means the lower the pH. So the more H plus ions, the lower the pH of the solution. Now to find pOH, similar equation, pOH is equal to the negative logarithm of the OH minus concentration, and the concentration of OH minus ions is equal to 10 to the negative pOH. Now combining the pH and pOH ideas together is this sort of last subset of equations. The pH plus the pOH is equal to 14, or the concentration of H plus ions times the concentration of OH minus ions equals 1 times 10 to the negative 14. Let's start with our first example. Now I included our equations right here. So our equations are going to be on the right side of our screen here, so we have them for easy reference, and you have them in your notebook from the previous slide. So here's our first question. What is the pH of 0.026 molar HClO4? Now HClO4 is called perchloric acid, and you should recognize that from one of the previous slides. This is one of these strong acids. So this is one of the strong acids of the 6 that you will memorize. So that's important, and again, we're only talking about strong acids and bases today, but that's going to be important because calculating the pH of a weak acid or a weak base will be different, and we'll get into that in a future video. So we've identified that it's a strong acid, and here is the concentration, 0.026 molar HClO4. Now in order to figure out the pH, we're going to use this first equation here in our equations list. The pH is equal to the negative log of the concentration of H plus. So I'll rewrite that equation. pH equals negative log of the concentration of H plus. Now, the concentration of H plus, because there's only one, this is called a monoprotic acid, there's only one H plus in HClO4, then concentration of that H plus is going to be 0.026 molar. So our pH is equal to negative log of 0.026 molar. And if you plug that into your calculator, you will find that negative log of 0.026 is equal to 1.59. So the pH is 1.59 of 0.026 molar HClO4. Now a great way to check your work is to note that 1.59, that is acidic. It is less than 7, so therefore that is acidic, which this is a strong acid, so yes, it should be acidic. Next, I'm giving you this example for you to work out on your own. So the example is, what is the pH of 2.5 times 10 to the negative 3 molar HCl? So please pause the video now to find that pH on your own, and I will show you the solution when we come back. If you have found that answer on your own, feel free to play the video now as you are, because here is the answer here, and I'm going to blow it up and make it bigger. So you take the pH as the negative log of the concentration of H+. The concentration of H+ ions here is 2.5 times 10 to the negative 3 molar. You do the negative log base 10 of that, and you should get the pH of 2.60, which is acidic because it's less than 7, and HCl is a strong acid. Here's the last question we will do together. So the question is, what is the pH of 0.018 molar BaOH2? I'm also asking, what is the pOH and what is the concentration of OH minus? Now, first thing to note with BaOH2 is that this is a strong base. This is a soluble metal hydroxide. Here's the metal ion, here's the hydroxide ion, and it is soluble. So this is a strong base. Notice we also have our equations on the right side for your reference. Now, when we calculate the pH of bases, it's always going to require an extra step. And so what you want to first think about after identifying that it's a strong base is the ions present. So when BaOH2 comes into solution, it's going to break up into one Ba2 plus ion and two OH minus ions. Forgive my handwriting, please. So again, we've got one Ba2 plus ion because there's only one Ba here, but there's two OH minuses. So our concentration then of our OH minus is going to be double the 0.018 molar. So because there's two OH minuses, our concentration of OH minus ion here is actually going to be 0.036 molar. That's our concentration of OH minus because, again, we've got two hydroxide ions in one BaOH2. So we take our 0.018 molar and double it to make it 0.036 molar. Now, because we have the concentration of OH minus, we can go to our equations here on the right and see that with the concentration of OH minus, we can find the pOH. So pOH is equal to the negative log of the concentration of OH minus. So the pOH is equal to negative log of our concentration of OH minus, which is 0.036 molar. If you do negative log of 0.036, you should get 1.44. Notice that is the pOH, not the pH, the pOH. So there's our pOH, and in order to calculate the pH, we're going to go to this equation here. pH plus pOH is equal to 14. So I'll write that here, pH plus pOH is equal to 14. So if we know our pOH is 1.44, the pH is equal to 14 minus the pOH, or pH is equal to 14 minus 1.44, which is going to give us 12.56. So that right there is our pH of this strong base of 0.018 molar BaOH2. Notice that a great way, again, to check your work. This is a base, and notice 12.56 of a pH is higher than 7 on the pH scale, so that is indicative of a basic solution. Nice work, chemists.